Anybody been watching Venus going past the Pleiades?
Yes.
Yes. Yeah.
Yes, very good.
Yes.
Beautiful.
Nice
And
picture there, but
And of course, if you've got a telescope on it, this is the view yesterday. So it's starting to go to a thick crescent. So yeah, and it should get bigger and bigger. So why won't it let him in?
Channel 4 news until.
Okay, so just looking at what we've got. Oh, there you go. Chris has sent some links to the programs. So this Thursday, we got Xabi talking about imaging the ISS, just using the webcam and a Dobsonian, I believe, is what he uses to do that. And then, of course, got Mike's Space Go Watch event on Saturday, where I'm going to do my Apollo 13 talk.
go space watch, Dave. You got to go in the space.
Sorry.
Yeah, got a bit dyslexic.
I did, yeah. It's the fingers that are dyslexic. Anyway, yeah. And then we got Terry Lovejoy next Tuesday. He's going to be talking about hopefully the comet, but I don't know if you've seen the news lately. It looks like it's fading, and the nucleus itself might be breaking up. So that could be bad news for us, hoping we're going to see a really nice comet in a month or two's time. Then Thursday, the 16th of April, general chit chat. If you've got anything you want to share, or if you want anything to show, then let me know. Somebody's already sent some stuff in for me, so that'd be great. But if you've got anything you want to shout out and show, please let us know. And then 21st of April, we've got Paul Fellows talk about Hawking's black holes and the edge of physics. So something for everybody, hopefully there. And if anybody got any suggestions, then please let me know, and we'll see what we can do. I'll see what I can find out and get somebody to talk about.
Dave, a quick question. Kev here. Just occurred to me, what is the number of people limit that can join the Zoom group?
Well, on the account we've got, it's 100. If you wanted 250, you'd have to have a minimum of 10 hosts, and that's £15 a host, which is just a ridiculous amount of money.
Indeed. And how many have we got on tonight?
We've got 57 on at the moment,
Okay.
but I'm also getting it to stream to YouTube. So if anybody can't get in, they can actually see what's happening.
Yeah, no, the crazy thought just occurred to me that John might be trying to get in, but he's over the limit. So
No, we're not over the limit yet. No, I'll kick a few people out first. Are we able to do that? I don't know if we are. Oh yeah, look, we can put people
first in, first out, or something.
We can put people in the waiting room. So yeah, so he's not locked out yet.
Good.
So hopefully, when John does arrive, this is what he's going to be talking about, and he's according to the website, he's Deputy Geology Geophysics Imaging Node Leader based at Southwest Research Institute, Boulder, Colorado. But he's from the UK apparently. And he's going to talk about 1 billion miles beyond Pluto. Can you imagine 1 billion miles beyond Pluto? That's just incredible, isn't it?
Of interest, was this the same guy that did a talk a couple of years ago at Astrofest?
I don't know.
I think it was.
Was it?
Yeah.
I think I remember his name.
If it is that guy, it was good.
Right, excellent, good. And if anybody, I don't know whether he's going to mention this later, but if you haven't, oh, hello, that's doing strange things. You can't see the book. Hold on, let me change my screen because that's silly. Hold on. I was going to show you. Yeah, if you. Anybody seen this book, Chasing New Horizons by Alan Stern and David Grinspoon? It's all about what they had to do to get the mission up and running. And it is an absolutely brilliant book.
Yeah,
I couldn't put it
down.
down.
Through it at the minute.
Sorry?
I'm halfway through it at the minute.
Halfway through, yeah, and it's absolutely amazing, the politics and everything they have to go through just to get a
Yeah.
mission up and running is incredible. So that's
Yeah,
well worth people having, I think, anyway. Oh, here he is. He's arrived. Excellent.
Hello.
Right, let him settle in, and then we'll. Hello, John.
He's on mute at the moment.
He's on mute. Right, okay.
Hi, can you hear me?
Hello, John. How are you?
I am good. I'm so sorry I got confused with the time zone despite my best efforts.
Oh, that's fine. I've been trying to fill in a little bit for you, so that's fine. Excellent.
right.
Right, I'll stop sharing my screen then.
So give me a second here.
Yeah, so you're all familiar with how Zoom works, I guess.
We use it a lot for our stuff.
I'm sure
so
you
yeah.
do, yeah, like most of us these days, yeah.
Mhm. So give me a sec.
What I will do, I'll if I can get people to mute their microphones and turn your webcams off, just so we save a bit of bandwidth while John's speaking, if that's okay.
So hopefully you can see me now. Oh no. There we go.
Yeah, can see you now, John. Hi, John. Hold on,
Hi.
I'll leave my face on for a little while. There you go. Good day. Good day to you, John.
Hi.
Thank you very much
Good.
for agreeing to speak to us. Really, really appreciate it.
Good to see everyone. So I'm going to share my screen. And let's see. I have to make sure I got the right screen first. So.
It's gone very quiet out there.
Yeah, I'm fiddling with stuff here. Give me a sec.
That's okay.
And there's often this weirdness with sharing screens when you're using PowerPoint. So. Okay, so hopefully you're seeing my full screen and you are.
Yep, we certainly are, John. Okay,
Yeah,
I shall mute my mic now and leave you to it. Is okay?
All right. Okay, so thanks all for joining this. I hope everyone is safe and well. It's a weird time, but I'm glad it gives me an excuse to talk to you all and hopefully provide a little distraction. So I'm going to talk about the New Horizons mission that is currently exploring the outer solar system. Of course, we flew past Pluto in 2015, but we've since then been exploring out in the Kuiper belt. And a lot of you are probably very familiar with the Kuiper belt, but I'll just give a bit of background for those who aren't. So this is what the solar system looked like in 1990, when we knew about what were then the 9 planets, and we had the outer giant planets in these nice, well-behaved orbits, and then Pluto in this kind of crazy orbit that was not really fitting in with the rest of the solar system, and nobody quite knew what to make of Pluto at the time. But starting in 1992, we started discovering a bunch of other stuff out here. And So the yellow dots that you may not see very well are now some of the, probably a couple of thousand now, of other objects we found orbiting beyond Neptune that we call the Kuiper belt. And we now know that Pluto, instead of being this oddball on its own out there, is simply the largest and brightest member of this vast swarm of objects out there. And to show them a little better, rather than just showing the objects, I'm going to show their orbits. And you see there's just a huge mass of objects out there. We think there's at least 100,000, probably more than that, out beyond Neptune. So going back to this view, you see that it's still pretty empty out there, but there are a lot of objects that are just still millions of miles apart, just because there's so much space out there. And so now we know that Pluto is still the largest by a smidge out there, but there's Eris that is much further out and nearly as big, and a whole bunch of other objects that are a little bit smaller than Pluto that are still of substantial size and are very interesting worlds in their own right. So we are very interested in these. They're remnants of the earliest history of the solar system that are out in cold storage in this distant part of the solar system where they're really not disturbed very much. So they tell us a great deal about what's going on out there. And so even before the Kuiper belt was discovered, we wanted to know what Pluto was like, and it was already, we knew it was a pretty interesting world in itself. So here is, the reason we needed to go to Pluto is because it was so hard to find out much about it from the Earth. And here's the Hubble telescope, which has been the most powerful telescope we've had for looking at small, distant objects. This is the best picture of Pluto taken with the Hubble telescope. And it's really not terribly enlightening. You could see that there's some areas that are bright, some areas that are dark. You kind of get a feel for the size of it. But you're not going to do much science on an image like that. And so we really wanted to go there and find out what Pluto was like and also explore the rest of the Kuiper belt. So here's our spacecraft. This is the New Horizons spacecraft that we built in the early 2000s to explore Pluto and the Kuiper belt. And I'll just give a quick tour of the instruments here. Hopefully you can see my pointer here. So the main antenna, this is what we use for sending data back to Earth, receiving signals from Earth, but it's also, we use it to measure radio signals, how they're affected by Pluto's atmosphere, how they're affected by this, how they measure how the spacecraft is changing trajectory due to gravitational influences, so we can measure gravity with it too. We have a couple of plasma instruments here that measure the solar wind, which we can now track way out into the distant regions of the solar system that are hard to explore in other ways. Our biggest telescope is actually behind its lens cap here. You can't really see it in this picture, but it's an 8-inch telescope, which takes black and white images, but very detailed images, very high resolution. Underneath the spacecraft, we have a dust counter, which is a instrument built by students at the University of Colorado to measure dust impacts on the spacecraft and understand how much dust there is in the outer solar system. And then one of our real workhorses here is the Ralph instrument, which includes a color camera. And also the LISA instrument is an infrared instrument, and that measures spectra of the objects we're looking at and can tell you about their surface compositions. And then finally, we have an ultraviolet instrument that tells us about the temperature, about the composition of Pluto's atmosphere and other things out in the outer solar system. So we have a pretty wide range of instruments in this very compact spacecraft about the size of a grand piano, and it's a pretty powerful payload. So here's the spacecraft being encapsulated in the fairing of the rocket in late 2005. And here's that whole encapsulated package being brought at Cape Canaveral in Florida to be mated on the top of the rocket. This is an Atlas V rocket. It was the most powerful rocket that was available at the time. And here we are finally launching on January the 19th in 2006. We have a pretty small spacecraft, as you can see, and a very big rocket. So that gave us a really fast trajectory. It was actually the fastest spacecraft ever to leave the Earth and reach the moon's orbit in only 9 hours, compared, say, to the Apollo astronauts who took 3 days to get there. So this was really a pretty spectacular thing to see. I was very thrilled to be there to watch that spacecraft take off. And here's our trajectory. As I said, we launched down here by this close to the sun in January 2006. Then flew past Jupiter in 2007, just a year after launch. It only took us a year and a bit to get to Jupiter. And then we had this long 8.5-year cruise out to the Pluto system in 2015. And then continuing on into the Kuiper belt beyond Pluto, that we're still there, we're still exploring. And so it was very useful having this Jupiter flyby just 13 months after launch. The main purpose of that was to give us a gravitational boost on the way to Pluto, but it also gave us a really good chance to check out our instruments and take data on the Jupiter system when we did some new science there. But many spacecraft have been to Jupiter before. So mostly we were just learning how to fly our spacecraft, do real science with it. And it was a really important shakedown for us. So here's just an example of the Jupiter data. I won't say too much about it, but here's Jupiter's moon Io, one of my favorite places that is a very volcanically active world. And this is an image here taken with our black and white camera, the lorry camera. So this camera down here, and you see quite a lot of detail. You can see mountains along the terminator here. You see this huge volcanic eruption and the glow of a volcano on the night side of Io, and a big cloud of volcanic debris being blasted into space above that. The color images we take with the MVIC camera aren't as detailed, but you can see the orangey yellow color of Io. You also see that volcano is glowing red, as you would expect hot lava on a volcano to do. And then this cloud of debris is a blue color. And then the infrared instrument LISA is, again, less detailed still, but you're seeing the glow of all those extra volcanoes on the night side. So you're not just seeing this one big eruption, which is incredibly bright, but you're seeing dozens of others on the night side from all the active volcanoes on Io. So we can really see a lot of different things with our instruments, depending how we, which instrument we use. So then we had a long cruise to Pluto. It took us 8.5 years to get there. We had a birthday cake for the spacecraft every year as an anniversary of the launch. But we were also very busy all that time, just planning what we were going to do when we got to Pluto. It's a 4.5-hour light time to send signals to Pluto, 4.5 hours back. So you've got a 9-hour delay between when you tell the spacecraft to do something and you get any feedback as to whether it worked. So you can't do this real time. Everything is pre-programmed. We developed this very complicated series of observations, how to point the spacecraft at the different targets around Pluto as we flew past. And so that when we got there, we would be ready to do everything perfectly. And we even rehearsed the whole sequence on the spacecraft a year or two before we got there, and had the spacecraft do all these maneuvers, take pictures of nothing, just to make sure everything would work. And then finally, in early 2015, we started approaching Pluto, and it was an incredibly exciting time. This is a display on one of our computers in our science area, just showing Pluto every 6 days as we got closer and closer. Pluto rotates every 6 days, so you keep seeing different sides as it rotates, but every 6 days you see the same side. But as you go from one 6-day period to the next, it's getting closer, you're seeing more and more detail, and it's looking more and more intriguing. And we saw this beautiful heart shape on Pluto that seemed very welcoming, but we had no idea what it was at this point. It was just a very intriguing marking that we really wanted to know more about. And then we got into the real encounter, and we had all the scientists there and working closely together. Here's some of the navigation team who are responsible to delivering us to Pluto at the right location. Here's Alan Stern, who's been the mastermind behind the whole mission. He's the chief scientist, wearing a Pluto hat that we had for a party on the approach, and the project manager, Glenn Fountain, here at that same party. They're giving the 9-finger Pluto salute here. And then here we are the night before we got to Pluto, some of us staying up till 3 o'clock in the morning, processing the images that were coming in, then getting the first close-up look at Pluto. And here's the day after the encounter, all gathering around my computer in this case to see those first high-resolution images and just being amazed by what we saw. And so here is Pluto. I don't know how this zoom will work on the WebEx, but hopefully you can get a feel for how the amazing amount of detail we're seeing in Pluto once we started getting the close-up images down. All these amazing colors due to different, very varied surface with lots of different compositions on it. And this vast area here, which is part of that heart-shaped marking that we saw on approach, which is a huge sea of frozen nitrogen that is convecting. There's enough heat from the interior of Pluto that you're seeing these patterns on the surface that look like boiling soup on a stove, and for the same reason that there's heat coming up from the interior and making this nitrogen ice, which is quite soft, bubble around. We're seeing huge mountains here. These are the height of the Rocky Mountains that are made of ice. We're seeing ancient regions with craters, big fractures here, just an incredible variety of surfaces. This is a region where we see something that looks like it may be an ice volcano. It's a big mountain with a hole in the middle of it. More mountain ranges, all kinds of strange stuff that's completely unlike anything we'd ever seen before. Not many craters here, which means that this part of Pluto is pretty active. Geology is happening. It's erasing craters, producing new landforms. So Pluto is a really active world. Here's a region on Pluto where we see glaciers. If you can see, this is a highland region, and you see streams, flow lines coming down onto this low plain. You can maybe see them better here as the nitrogen that's coming out of the mountains is pouring down into the vast nitrogen plain and acting just like glaciers do on the Earth, except it's frozen nitrogen instead of frozen ice. And here is Pluto's big moon Charon. Charon is about half the size of Pluto, a very different world. You can see it here as being intensively fractured. There's a northern region here that is covered in huge fractures, the size of the Grand Canyon or larger. And then a region down at the bottom here that is smoother, we think is a vast outpouring of ammonia water slurry sometime early in Charon's history that covered over this region, covered up all those fractures. But you've seen craters everywhere, and this means Charon, unlike Pluto, is a pretty old surface and has been probably pretty quiet geologically for billions of years. And then Pluto not only has this big moon Charon, but it has 4 small moons, Styx, Nix, Kerberos, and Hydra. These are the best images we got of those compared in size to Charon here. It's really, these are irregular worlds that are not round like Pluto and Charon because they just don't have enough gravity to form a nice round shape, but they're very interesting in themselves. We don't really know how they formed. But eventually we had to go leave Pluto behind and carry on out further into the Kuiper belt. This is one of our parting shots, which I think is everybody's favorite picture that we took during the Pluto encounter. This is looking back at the backlit landscape, this huge nitrogen ice field here, the mountains sticking up on the horizon. mountains as high as the Rocky Mountains. And then the atmosphere, Pluto has a very thin but very deep atmosphere, filling the entire sky here with these layers of haze. And so this is as though you were looking out a plane window over the over Pluto's landscape if you happen to be right there. And as we pulled away further, you see that this haze is this beautiful blue color. We took an image with our color camera, and so there's perfect ring all the way around Pluto, this very deep atmosphere backlit by the sun. So Pluto was beautiful. We would have loved to stay, but we were continuing on out into the Kuiper belt, and we wanted to explore not just this biggest world in the Kuiper belt, but some of the more representative worlds, these hundreds of thousands of small worlds that were also out there and are going to tell us something about the early history of the solar system. And so here's Pluto is kind of its orbit is eccentric, but when we went past it, it was close to its closest spot to the sun. So most of the Kuiper belt was further out. And we had this long cruise out through the Kuiper belt that we're still involved in now, taking several years. And it looks here from this star's impression where you could hardly avoid running into one of these objects. But in fact, these are millions of miles apart, these tiny worlds. And we had a problem that we knew we were going to have, that when we launched, we didn't have a specific object we wanted to, that we could get to. We knew there were lots of worlds out here. We were pretty sure we could find one that was going to be close enough to our trajectory that we could reach it with the spacecraft. But we hadn't actually found one because there's so many objects out there. It's in a part of the sky in the Milky Way where it's really hard to search for objects. And so we had actually to go to the telescopes once we were already in flight and start looking for objects that are along our trajectory. And if there's an interesting looking object over here, that's no good, because we'd have to make a sharp turn after Pluto to head over this way. But in fact, we only have a little bit of fuel for maneuvering. We could only change our trajectory by about ½ a degree. So really, we had to find something that was pretty much along this trajectory line or just off a little bit from it. So that was a pretty challenging endeavor. And we got some of the biggest telescopes in the world. Here we are in front of the Subaru telescope on Mauna Kea in Hawaii. One of the world's largest telescopes has a huge wide field camera that's really good for searching large areas of the sky for moving objects. And we looked for 4 years with these big telescopes. We had a bunch of astronomers helping us out. We found dozens of objects out there, but none of them were quite close enough to our trajectory that we could reach them. So we had a problem, and it was only a 1.5 years before we got to Pluto. And we had to make our course correction right after Pluto to reach one of these objects, and we hadn't found one yet. So we called on the biggest gun that we had, which was the Hubble Space Telescope, which of course we used to take those nice pictures of, well, those pretty fuzzy pictures of Pluto pretty early on. But now we could use it to search much deeper than we could do with telescopes on the ground for some moving object that was close enough to our trajectory that we could reach it. And the one problem with Hubble is it has a pretty small field of view. It doesn't have one of these big wide angle cameras. If you want to search, we actually had to look at 80 different fields on the sky. We took a lot of time on Hubble, and we pieced together this coverage of this whole area by just patiently looking at one piece of sky after another. And this image is just half of one of those fields of view. You see, it's full of stars. That's because we're looking in the Milky Way. This is just an area with far more stars than there are Kuiper belt objects. And seeing anything between those stars is really challenging. And so I'm going to cheat here. I'm going to zoom in on this little area here, which is where we eventually found an object that we could reach. And this is an image, one image of that field. And most of these big blobs you can see here are stars. Some of them are cosmic ray hits where some particle has just run into the camera and made a spurious flash of light. Here's the next image. We took a sequence of 5, and the next, and the next, and the next. And I don't know if you can see, but there's an object right in the center of the field that isn't moving. And it's right here. That's because we're tracking at the rate that we expect the Kuiper belt objects to move. And this thing turns out to be a real object. The stars are moving. This is not moving. The cosmic ray flashes come and go. But this was the object that my friend and colleague Mark Bowie called me up on a Friday afternoon in June 2014 and said, you better come down to my office and see what I've got here. Because he realized this was something real. It was moving about the right speed to be an object that we could maybe reach with the spacecraft. And we then tracked that through the whole summer of 2014, and we got a good orbit, and we eventually found out that, yes, this was an object that we could reach with the spacecraft. We found a couple of others, but none of them were as close to our trajectory as this one. This we could reach and still have lots of fuel to spare, so that was really good. And originally, it just had a preliminary designation, 2014 MU69. And this is where it is. This is its orbit around the sun. It's quite circular. You see, Pluto here has this crazy tilted, elongated orbit. But MU69 has a very circular orbit. It's a flat orbit. It really fits in well with the orbits of the other planets. And so that makes it a very special object out there. It's what we call a cold classical object. Cold doesn't mean it is physically cold, though it is that cold, but it means its orbit is very undisturbed and quiet and orderly. And that it makes it really interesting because it's one of a large class of objects, the ones that are colored orange here, that are orbiting out there that have, we know from their orbits, have to have been undisturbed since the formation of the solar system. They formed out there, they've just been orbiting quietly ever since. Nothing much has happened to them since then. So we were very excited that we could go reach one of these objects and see what they were like up close. It was going to be like nothing we'd ever seen before. We knew that much. So here we are. We reached Pluto in 2015, and we were going to reach this object. It turned out just by coincidence on New Year's Day 2019. So we had 3.5 years from Pluto to MU69. And eventually, actually, after the flyby, we got a proper name for this. It's now called Arrokoth, which is a Powhatan Algonquin word for sky. This is a naming ceremony that was held at NASA headquarters by a member of that tribe and a bunch of the people who had helped discover it. We used a word from this language because we wanted to honor the state of Maryland, where those tribes had lived and where the spacecraft was built and was operated from. So we all go to Maryland to actually do these encounters. So we had to set a course to Arrokoth, and in November 2015, which is only about 3 months after we flew past Pluto, we fired our engines. We were just about here, and we did a deflection maneuver of about 1/4 of a degree, just a little bit of a nudge, but that was enough to take us out towards a direct encounter with Arrokoth on January the 1st, 2019. So then we had a great deal of work to do, and we only had 3 weeks to do it in, 3 years, sorry, to do it in, to plan all the observations we were going to do when we got there. And by the time we get to Arrokoth, it's a 12-hour round trip light time. It takes 6 hours at the speed of light for a signal to get from the Earth to the spacecraft, and 6 hours back. And so it was even more important to plan everything else out in advance and leave nothing to chance in the encounter. So we had lots of meetings and lots of discussions. Here's just an announcement for one of our meetings where we were deciding what our trajectory was going to be. Were we going to fly by above or below? How close were we going to be? All these things had to be worked out. Here's some of the spacecraft team working out some of the nitty-gritty of just how you command the spacecraft to do exactly what you want at these distances. And eventually we came up with a plan of all the observations we were going to do. We decided to fly by at about 3,500 kilometers. That's 4 times closer than we came to Pluto. Because it's such a small object, this object is only about 30 kilometers, 20 miles across, that we wanted to come much closer so we could get decent pictures of it. But that made the navigation really hard. But here is our plan, and we're doing an infrared scan. We're measuring the temperature, then a color scan, and then another infrared, another color, then our best black and white images when we're close in, and then looking at the night side, thermal observations and other observations going outwards. And all this happening very quickly. This is only 15 minutes between these time ticks. So it's all over in a couple of hours. And we're not in direct communication with the spacecraft. It has to do everything that we want exactly at the times that we tell it to, and we hope everything goes smoothly. One thing we were really worried about is because this is such a tiny object and we're flying so close to it, is we better have our cameras pointed in the right direction. And there's another mission that I'm working on that's has a fancy control system where it can actually lock onto a target and then just follow it through the encounter and make sure the cameras are pointed at it. But on New Horizons, we didn't have that capability. We have to tell the spacecraft to point blind. We say, point at this, right ascension declination, and hopefully the object is there. And we've got this very narrow field of view camera that's like looking through the end of a very narrow drinking straw. And we were really afraid of the case where Arrokoth is over here, but our cameras are pointed over here. And that would be really bad. And we wouldn't know till too late whether we could do anything about it. So the navigation, figuring out exactly where it was so we could point our cameras in the right direction was really crucial. And we really sweated bullets over that. So here we are in August 2018. We took our first images from the spacecraft that we hoped would show Arrokoth. This is one of our images. And again, we have the Milky Way in the background. This is somewhere in Sagittarius. So there are just thousands of stars crowding in this image. And we expected Arrokoth to be right here in these crosshairs. And you can't see it because of all these stars. So we had to do a lot of processing to correct for that and show where Arrokoth should be. And when we did that and we subtracted the stars, and here it was. Here is something that isn't a star. We did not remove it by a star subtraction algorithms. And here it is right in the crosshairs, exactly where we expected it to be. So this was really good news that we were really pointed in the right direction. And that made us all feel a lot better. We still had a few months to go. We were continuing to track it with the spacecraft all the way in. And so we had a lot of meetings with the navigation team. Here is one of the charts that we looked at a lot that's basically showing the sky ahead of us. Here's a box where we need the spacecraft to fly through in order to have everything aligned properly, have all our pictures in focus and pointed in the right direction. And here are various estimates as where we thought the spacecraft was at that time. And it's not in the box, which means we're actually a little bit off course. And this was a time when we were deciding, okay, we have to fire our engines, do a little bit of a tweak to our trajectory to get us back in that box. And we had a lot of meetings like that, working out those details. And I was not really in the critical loop for this. I'm not a navigation expert, but I was in the meetings and was just, these meetings were really riveting. And I really felt like this is like Captain Cook in the cabin on the Endeavour 250 years ago, wondering, well, we just got a new longitude reading. It's not agreeing with our old longitude reading. Do we need to change our course to get to New Zealand and so on? It's really just the same game that explorers have been playing for thousands of years, and we're continuing that tradition. So here on the science team area, we've got on our countdown on the whiteboard, it's 24 days till we get there. And we had a lot of speculation about what Arrokoth was going to look like when we got there. We'd just seen this dot of light. This guy, Mark Bowie, who actually discovered Arrokoth, had done an experiment where we watched it pass in front of a star in occultation and got some idea of the outline. We were trying to get what the three-dimensional shape of it might look like from that. So while we're on the approach, he's using really high-tech tools. He went out to a store and bought some modeling clay, and he's trying to make shapes that might match that outline that we saw in the occultations. Here's another view and how it might spin as it rotates. So there's this fun mixture of really high-tech and really low-tech stuff. we got kind of creative as to what kind of shapes it might be at some point. And so by the time we got there, this is just happening around Christmas. We had a Christmas tree in the science room. We had various possible shapes that it might be under the Christmas tree, waiting to unwrap and see what it was actually going to look like when we got there on New Year's Day. So we took a little time off. This is on Christmas Day. This is 7 days before we got there. Here's Mark Bowie again, and the mission operations manager and the chief engineer, having a little bit of R&R before to celebrate Christmas before we actually finally got there. But then it was back to working with a vengeance for those last few days of the approach. And because of this 6-hour light time each way, and the fact we wanted to have the best possible last-minute information to decide on when to point our cameras, we had to have meetings at crazy times. So we got our best pictures of the spacecraft down from the spacecraft down to the ground around midnight. We had like 4 hours to process them, and then at 4 a.m. we had to make a decision whether we were going to change the spacecraft pointing and fine-tune our cameras so that they were pointing in the exact right direction. And so this is at the end of that meeting at 4 a.m. That gave us just enough time to get that information back up to the spacecraft, to have it adjust its pointing and make sure our cameras were pointed in the right direction. And then we all got not nearly enough sleep and got back to work for the last couple of days of the flyby. And then the next day, we finally got pictures where it wasn't just the dot, it was starting to show some detail. And I think I woke up after that 4 a.m. meeting about 10 a.m. and downloaded these images from over the hotel wireless internet. And so, oh yes, we're now finally starting to see some shape to it. And we could see it was actually not a round thing at all. It was pretty elongated. And then the next day, we were twice as close. We're now only a day out. And we can see that it's not just a single elongated object, but it's two blobs with apparently a narrower bit in the middle. So that was pretty exciting. That was telling us we had some really interesting object here. And then, of course, it was New Year's Eve. Just 33 minutes before our close flyby, we celebrated New Year's Eve, and we had a party at the encounter. Here's Alan Stern in the middle of all these kids. So that was fun. And then we had to wait because the spacecraft was busy taking data at that time, and it wasn't radiating any information back to Earth. So it wasn't until the following morning, on January the 1st, that we got the information from the spacecraft, just a quick hi, everything's fine message. And that told us the encounter had been successful. The spacecraft had not failed in any of its observations. It had taken all the data. And so that was another big celebration. And here we are celebrating that moment the following morning, 11 a.m. But we still didn't have any data from the spacecraft at this point. Just to relax, everything's fine. We hadn't actually seen the images. We didn't even know if they were properly pointed. And so we really had to wait a few more hours to get that information. We went to had lunch, went back to the science area, and then we started to get that first picture down. And we were just all holding our breaths at that point. Here's, the image comes down in slices because it's a pretty slow process. It takes about an hour to get an image down. And so this is the first slice of the image. And we were very excited by this, even though you can't see a thing in it, because this streak here, and this streak is an artifact of the camera. It's telling you that you only see this streak in there if there is actually something in the image. There's something up here. And so we knew at this that we were seeing something in the image, even though it wasn't down yet. And so everyone's hitting refresh on the computers, trying to get the next slice of the image, see that first glimpse. And then just about 5 minutes later, a guy at the back of the room yells, "I got it." And everyone just crowds around his screen to see what we got. And here's everyone doing here's the view from the other side. And here's the picture. You can't see it very well here, but this was our first glimpse of what Arrokoth really looked like. And when we put that on the big board, we can see it properly. You can now see it's really this extraordinary object. It's got two lobes here that are joined by a narrow neck, it looks like two objects that formed separately and came together. And so we were very happy, not just that it was such an extraordinary object, but that everything worked. It was beautifully centered in the pictures, lots of hugs, lots of cheering. And then Mark Bowie, who'd predicted that it might have this kind of shape, is very happily showing his model of the shape against the outline of what it actually looks like. So he was very happy his models have worked. Here's a little bit better view about the best view that we had on that first day. It's about 20 miles, 30 kilometers across. And this intriguing white color between where the two objects came together. But we knew we were going to get much better pictures than this. We just had to be patient for them. So here's one of our scientists, Bill McKinnon, leading a discussion of how the heck you form an object like this that seems to be made of two objects stuck together. And we really were just speculating and waving our arms pretty vigorously at that point to try and understand it. But we knew we were going to get better data with time, and so we had to be patient for a few more weeks to get the best images down. And so we took quite a few gigabits of information on the spacecraft, and the rate at which we get the data down is like a 1989 dial-up modem. And so it takes weeks to get all the data down. And in fact, we're still getting some of the data down now. We got the highest priority stuff early, but we're still completing getting every last bit down. But then I hope you can see this over the Zoom. But this is a rotation movie that we took. As we approached it, we were watching it spin. You can see the images get more detailed as we got closer. But this gives you some idea of the three-dimensional shape of it. And this was very important for trying to figure out what it was really like. You can see that its pole is pretty much pointing at us and it's spinning in the sky. So we're seeing similar sides of it all the way along, but we do see some variation. And then here's our closest view of the object. It's really like nothing we've ever seen before. It's a very smooth surface. It's got these lumps that seems like it may have been mushed together out of smaller objects. We see a few craters here, which indicates this is a pretty old surface, but the craters haven't destroyed the original shape. They're quite lightly cratered. Partly this is because this is a very ancient object, but it's in such a quiet part of the solar system. Things just don't run into it very often and don't produce many craters. We got color images. This is the color and the black and white, and then a merger of the two. The color of the two sides is this reddish brown color, which is very distinctive of these cold classical primitive objects out there in the Kuiper belt. And the two sides are identical color, suggesting that they formed from pretty much identical material close to each other in the solar system. And then we got stereo images. And hopefully you can see the animation on the right, which is two of those images being merged, being tweened from one to the other, so you can get some idea of how it would look if you were just rocking your head backwards and forwards to get some idea of the three-dimensional shape. And if you're good at cross-eyed stereo, if you can cross your eyes, you might see a beautiful three-dimensional rendering of these two images that gives you an even more visceral picture of the shape. And these objects are not spheres, they're pretty flat. And they're stuck together pretty much along their equators. And this image actually shows the shape. We have these two blobs that are almost perfectly aligned with each other. There's really some tidal forces have brought them together, aligned their equators before they came together. And then they've come together very gently so that their shapes are not destroyed or disturbed by that merger. So they're forming in this very quiet environment. And how we think this happened is a form of gravitational collapse. Somewhere out there in the outer solar system, 4.6 billion years ago, you had the gas and dust of the solar nebula. And there was an accumulation of the dust out there in the gas. The gas pressure, we think, brings the dust together until there's enough of the dust that it starts to collapse gravitationally, but it's doing this fairly slowly, and you have all these materials coming together, building up larger objects. until eventually you just have two objects orbiting each other and looking kind of like this, and they're locked together by their tides, and so they all align with each other perfectly, and then due to the gas that's left, they gradually slow down, spiral in, and eventually merge to produce something like this. And this is a key process to how the planets formed. In order to make planets the size of the Earth or any of the other planets, you need to start with tiny grains of dust, and you need to bring them together and make them stick. And for a long time, there's been a big problem that if you have objects that once they reach a certain size, even meters across, when they hit, they're going to smash up and form smaller pieces, break each other up. And you can't make planets that way. But Arrokoth is showing us how this process actually happened. It's this slow merge of things coming together in the gas. And this way you can build planets. And this is, therefore, we think, a pretty important step in how the heck we come to be here on this planet, how we came to be able to build a planet that humans could live on. And so that's the story that we got from our exploration of Arrokoth. We're still exploring the Kuiper belt now, looking at other objects from much larger range. But this is a pretty big prize to get from this additional exploration beyond Pluto, and we're very pleased with how all this worked out. So I'm almost done, but I'm going to try one more thing. One thing that's really fun about these encounters is you get a lot of publicity. You get to meet some very interesting people, and somebody who we got to know pretty well is Brian May here, who of course is the lead guitarist for Queen, but also has a PhD in planetary science. He did work back before he became a rock star on the zodiacal light. And so he knows his stuff. He's very much into stereo photography, which we've worked a lot. So he was part of our mission and was helping us out, doing wonderful publicity for us. And after the encounter, we worked with him to make a little music video where he did the music, of course. And we put together images from the encounter into a smooth movie that was able to show the encounter as it would be if we were riding along on the spacecraft. And I don't know how well this will work over Zoom, but I'm going to give it a try. So here is our first view looking at just the field of stars, seeing one object in the middle that is Arrokoth, and it's gradually getting brighter and getting closer. And you'll see it turn, and I'll just let it play.
We explore because we are human. And we want to know.
And there we are. That's what we've been doing in the Kuiper belt, and I hope that was enlightening. Happy to take questions.
It's rather nice that he can put his name to stuff.
Yeah. That bit, that last bit was.